Hey everyone, it's Alex Warner from CPP Uni, just checking in. All right, it looks like we're live. Hi everyone, we gonna start in a minute. Just I'm gonna let everyone to gather here, and today is gonna be another session on the standard library. It's confusing because here it says. Oh, all right. I'm gonna figure out my sound. It's very new for me and it's very nervous, so please bear with me. It's gonna be entertaining. It's gonna be a good evening today. All right, I see people in the chat. Hello, John. So let's start for now. Welcome everyone to first fully remote session on the standard library. I'm not sure if CPP Uni had any fully remote sessions before, but yeah, in the current situation, we have no other options rather than to go remote, and I'm gonna give you a bit of entertainment or edutainment during our self-isolation. So we figured out what should way to broadcast this be, and ideally it should be some kind of webinar solution, but we didn't have much time to research what it is. Therefore, for today, it's going to be a live YouTube stream, and we might find something better so people can ask questions. For today, I'm expecting questions to be here on YouTube chat. You're welcome. And also we have Tristan online who can help me with the questions just as the session goes. And questions on Slack are also welcome. If we can't address them during the session, I may catch up after it. So, yeah, as I said, for today is YouTube, and the further sessions on standard library will also appear on the YouTube channel, but we may figure out some better solution which would allow to ask questions like in real time and in person. So let's move on. Basically, I already mentioned Slack, and as we know, there is Slack is now a very popular app. And there is a special Slack for CPP, C++ language. You can get an invite on this website. Basically, you just need to leave your email there. And we've got a very special channel for London C++ University, where you can track our announcements and also ask questions about lessons, about problems, and so on. Everyone is welcome on Slack. Please check it out, and basically that's the best way to make sure that you don't miss out on any activities. And today we're talking about C++ standard library. It's third lesson, and like the presentation said, presentation title said session 4 because I have off by one error. Originally I promised that today is going to be associative containers, but after 2 previous lessons I figured out that we are already getting close to the algorithms, and people are getting excited about them, and people start really looking into them. Therefore, I decided I should probably give a quick taster of standard library algorithms, and then we're gonna move on to associative containers. So today we will be talking about algorithms, and the next lesson is going to be about maps and sets. And this is the outline of today's sessions. We will review what has been happening in previous sessions. and then we'll basically start cracking on algorithms. We'll start easy with our one of the first problems and of counting positive numbers. You may remember it from the previous sessions. And how do we apply algorithms there? Then I will explain more about like what are the algorithms and what are their value and like where to look for them. And then I think I also should talk about Lambda expressions, as they're really useful in application to the algorithms. Then we're going to have a deep dive with improving our problem of the palindrome, our solution of the palindrome problem. And then we just wrap up with a summary, and I'll give you another exercise. Revising what we were doing previously. First, I'm using unit tests in my code examples, and the idea that it's much more convenient and kind of declarative in the code, and then when I run the code, I'm sure that it's working as I expected, and I can check for more things than just with stdout, and also I don't need to eyeball them. I can really be sure that the things are working. So if you haven't onboarded with Sketch, I'll encourage you to do so. You can go to the GitHub page, and in the README, the very first line shows you how to grab the header for Catch, and then you can just put in your project folder, include it, and all the samples from this session become compilable and easy to use. And last time we were talking about strings, and this is just a reminder of what we were doing there. This is an example of a function which was splitting a space-separated string into separate words, and was returning an array of vector, a vector of strings, and we were talking about looking for a substrings with .find. We were talking about slicing the substrings with substr, and we also mentioned that this very special and post character is indicating that the string is not found. And if you want to revise more, if you want to get more information, you can find the slides on our GitHub. And unfortunately, the recording failed last time due to technical issues. But there is not much in particular, and also basically those who've seen it will today see examples that algorithms and iterators work better with strings rather than just these functions, and you'll be able to compare. And if you missed it, I'll recommend to just skim through the slides for the previous session. And now let's talk about the last time exercise. This was the exercise I was suggesting to count how many occurrences of a substring there is in a string. And this is the solution I propose. I hope people were able to figure out their own solution, and I will just dwell on the solution for a few minutes for you to read. I won't say it's the most elegant solution, but on the other hand, I had a goal to be able to fit it on the screen and only use the things which we have studied in the last two lessons. And problems like this show the importance of the unit test, and basically you make sure that the solution works if you just reproduce this and you don't need to try see std, see out for each occurrence, and can write all of them here and make sure that nothing is broken. So the questions are welcome, and if you have any problems with this, please follow up. As for now, we are gonna move on to the material of this lesson about the algorithms, and I'm gonna first bring up one of our first problems, which was counting the number of positive numbers in a vector, and that was the original solution, which also illustrates which I also used to illustrate the usage of catch. And basically we have a test case here, and we check that if we pass the array of all the positive numbers, we get the expected answer, and also if not all the numbers are positive, we get this. And the problem is pretty simple, and I decided to use it as an illustration how the solution can be even simpler with algorithms. So basically, let me introduce our very first algorithm from the standard library, which is called countif. And the purpose of the algorithm is it goes over the container and counts the number of elements for which predicate returns true. Predicate is basically a function which, given the input, says yes or no, and in this case it takes one element at a time, and therefore formally it's called unary predicate. And in our case it's a function which we call is positive. It's just checking if the number is bigger than 0, and that's the example of the algorithm. I need to pass the container to it and the predicate which I want to apply. And in order to pass the container, I pass the iterators begin and end, from where to where do I go, and also, as you may remember, dot end or dot cend looks past the last element. That's how all the standard library algorithms work. They go until they meet the end of the range, and they don't look at the element at the end of the range. And for each of the element, countif applies the predicate, and if the predicate is true, the count is increased, and after it looks up all the elements, it returns the number of the elements which satisfy the predicate. And obviously the results are the same, so that's the original solution. That's a solution with the algorithm, and we don't expect to see any changes in our results. But we can make it even tidier. If we don't use this function anywhere else, we can declare it in a magic way just inside of our function. And that's our very first occurrence of a lambda expression. I also see a question on the chat, what size t? And size t is an integer type which represents which allows us, which is good enough to store the value which can be the maximum size of a container, in our case a vector. It's unsigned, and that's basically what we need to know about it. It's really large. On some systems it's going to be over 2 billion, in some systems to be even further, as like 32 or 64 bits usually on the modern day systems. And it's basically the type-safe way to say unsigned int, which is enough to store number of elements in the container. So back to Lambda expressions. Here is just an example how I declared the same thing, the predicate, but inside my function. Therefore, the scope where the name is available is only inside my function count positive. And what's special about the Lambda expressions is that they start with square brackets. That's like the way you recognize them as like a very special syntax for them. And another thing to remember is if you give them a name, the type is always auto. Don't try to figure out their type. And the code works the same. And there is another slight improvement which we can do. Is just we don't actually need to give it a name, and we can use this in place. That's another great thing about Lambda expressions, as you can declare the function just in place, and if you use it in one place, you can pass a function there to the algorithm, and that's going to be the way how we are going to be counting numbers. I see Jonah is asking if I can use Lambda inside of COUNTIF, and I think this already should be the answer. And moving further, I just wanted to show the entire program as basically, if you also include algorithm header in this case, that's it. That's entire program. You can copy it and run it, and I hope it works for you. Worked for me, but with C++, you never know. Always depends on your setup. This is it. This is our very first usage of algorithms, and congratulations to everyone for getting here. And now let's talk a bit about what are the algorithms and why should we use them, because we originally had a working solution with for loop, and it's just was good enough. So the question is, what's the motivation to learn the algorithms and what the motivation to use the algorithms? And I would say the main reason I like them is that they are more expressive, and they basically have very descriptive names, and you can see, I can read the intention from the code. In this function, I'm counting, and also if it's not a standalone function and it's just a few lines in a bigger function, I can see, all right, I do counting here, and with a one line, I return a result, and I tell what do I want to do, and I don't dig into details how it's done. And actually, it's done pretty well and pretty reliable. It's a standard library which is used worldwide, and therefore it's well tested, it's well optimized, and you take the advantage of humanity wisdom accumulated over decades. And in general, as we were talking before about computational complexity, it's going to be quite well implemented from the point of algorithms and computer science, and therefore is often better than a naive implementation. These are my reasons, but still, like from the point of reliability, we do tests, and from the point of performance, is just also the advice is profile before you reason about it. But expressiveness is basically unbeatable, and if you know the algorithms and you read them naturally, it helps a lot. And also, if you are working with people who also use algorithms, it also helps a lot. The last bit about the algorithms is how do we use them, and there are two main headers which contain all the algorithms of the standard library. Algorithms is an obvious one, and there is also numeric, which has a group of important algorithms. I'm not gonna go over it myself, and I will basically um, refer to the John Bacara's work, who first made this amazing map, and also made a talk about a lot of algorithms and did a great overview. I won't expect to do such a good job as he did in terms of making a talk about all the STL algorithms in an hour. But this map is just like what's good about it. It gives an idea of what are the available algorithms and how they are grouped. And there are a bunch of algorithms which allow you to look for things, as we did countif and count, and also finding things. The same we did for strings. There is a generic find algorithm. There are also like what's called permutation things, which supposed to do change the order of things in the algorithm and also help you with permutations. There are things which do sorting and lookup and so on. There are set algorithms which work on ordered sets and can show you the difference between two set elements or do the intersection and so on, and they also will be handy when we start working with set types. But what's great about them, because the algorithms are generic, they also work just on basically sorted vectors or some other containers. And yeah, in general, I probably should put a reference to his great talk, and I really recommend to watch it. It's an amazing talk where he literally explains all the algorithms in an hour and does it greatly and in entertaining manner. And as for today, I will show just a few examples and try to go into details and try to make sure that the basics are familiar, and then on these basics, I hope you'll be able to build up the knowledge. Also, another advice I can give is that you can just go to cppreference.com and look at the algorithm header and the numeric header, and because of good naming of the most of the algorithms, most of them have really good names. Some of them are a bit confusing, but most of them have really good names. You will be able to guess, to understand what kind of things are done by the algorithms just from basically skimming through this page. So please take a look at that page. Please take a look at Jonathan's talk. And as for now, let's move on to the Lambda expressions. And as we're going to be using them in this lesson, and we're going to be using them in further lessons, I think it's a good time to talk about them and just explain a few principles, how they work, and why are they so nice. All right, so what is lambda expression? You already see in this magic expression with square brackets and the idea that you can define a function right at the place of use, and basically they were great with algorithms, or when you with some other things where you need to pass a function and be able to perform different actions dependent on different conditions. And it's just a few pieces of advice. Although you can write as long expression as you want, but I'd recommend to keep them small for better readability, and if it's something which is longer than a few lines, it's probably to be considered. It's probably better to consider making this a function. And also, just as I showed, if you need to give it a name, you need to specify its type, and it's always auto. Don't try to figure out what the type of them, and also don't try to like assign and reassign and so on when you're working purely with the lambda expressions. Just auto should be good enough, and if you need something else, unless you know what you are doing, you're probably doing something wrong. And I'm gonna give more details about how they work and how we can use them. First, the very introduction. Please meet an empty Lambda function. This is basically valid C++ syntax, valid C++ expression, which is going to do nothing. We declare a Lambda function here with square brackets, which show us the beginning of the Lambda function, Lambda expression. I keep confusing these things. Because it's just like the expression declares a function, but then the function which is declared is often, like at least in practice, called lambda function, or just a lambda. Expressions also just casually called a lambda. But because we are declaring a function here, I will, or at least a function object, I will be calling them functions informally. The formal term, the formal definition is lambda expressions, where I declare the function, but in practice, if they're functions and if they're declared by lambda expressions, many people tend to call them lambda functions. John has a note that the lambda functions can be faster because they can be inlined. That's correct, but also even if you declare the function and outside, declare a proper function and give it a name outside, with modern optimizing compilers, they also very likely to be inlined. If compiler sees that the function is used only in one place and it's short enough, it's gonna do it for you. And there is also inline keyword for functions if you know about these things, but from a few people who I heard talking about inline, compilers tend to ignore these keywords because they know better what to do about inlining function than a human would. So this may be true for some compilers, but very the advantage of lambda functions over normal functions is maybe true for some compilers, but very unlikely to be true for the widely used modern compilers, because they are smart enough to figure out how, if they can inline normal functions too. So back to our example. In this section we can do captures, and I will explain in the next slides what are the captures. For now, if you have no captures, it's just square brackets. Then these are the function arguments, like a type and a variable name, as in the example below, and those go as normal function arguments. And then function body, which is also goes as normal function body. The only difference from typical function declaration is that because it is an expression, we need to end it with semicolon, and and this applies both to a trivial lambda expression or to a proper lambda expression declaring a function. And then if I declare the function, I can invoke it as a function which does nothing. It does nothing. And if I do something more meaningful, it will return the sum of the elements. An interesting thing about the declaration of add is that I don't tell which type it returns, and compiler can deduce it automatically. Sometimes it fails, and in this case, or if we need to override the type which it has deduced, we have another option by using this arrow syntax after the function arguments. We can specify the type which we want our function to return. And here is the return type example, and I think like by default compiler would deduce the result type of this division as integer, but we can restrict it to unsigned char. And in this case, the compiler also will do the conversion for us, and still like works the same. But you can see here that the third line of the example, no way it is integer, it is actually unsigned, and not that in the next example I'm showing that wrapping works. So yeah, that's how we are returning a character type instead of integer. So that's these are the very first examples of lambdas, and now let's talk about captures. Here, first a disclaimer: I also use unit test sections. Just a reminder that the sections are run independently, and the execution finishes at the end of the section. So that's going to be the first branch. The second branch is going to be declaration of the number, then skip this, enter here, and exit here. And the third time the test is going to be run. It's all provided by the test framework. We declare the number, and then we enter at the last section and exit. So we have a few ways to capture variables, and the idea that basically either we want to take the value from outside and reuse it in our lambda, or we want to even make some side effects. And basically, in the end, the function just remains a function and only takes the arguments which we declared in the argument block. And in this case, all the lambda expression have no arguments there. And still, I'm operating the number which I've got declared outside of lambda. And if I just put the variable name there, I can use this variable name. If I had empty square brackets, this usage of number inside the function body won't compile, and basically if you write something what doesn't compile, the compiler will tell you that the name is not available, and you can put variable name there, and it's going to be captured by value. In this case, what I illustrate by this example, as soon as we declared the lambda, after I change the number, the value captured by the lambda doesn't change, and therefore if I invoke the lambda, I get the result with the old value at the moment of the capture, and I don't get affected by the change of the value. The opposite happens if I capture by reference. Syntactical difference between capturing by value and by reference is providing the reference sign, like it's kind of address reference, whatever sign, it's ampersand in front of the variable name. And in this case, I declare the lambda capture by reference. I then change the value, and the fact that I change the value affects the result, which may be useful in certain cases. Here my goal is to just change our syntactical options. And also what's important in our lambda, we can modify what we have captured by reference. Therefore, when I just invoke lambda, you can see that my number has changed. It's got +2 added. Another thing to point here is that when I'm declaring the lambda function, if I don't have any arguments to declare, to provide, I can omit the parentheses and just do square brackets and then the function body. These are the main bits about captures. There is a little bit more. The idea is that if you want to capture a bunch of things, You can there are shorthands for doing this, and if you want to capture everything by value, you can put the equal sign in the square brackets, and in this case it makes available all the variables which were available in the scope, and basically make them available by value. Same we can do for capturing by reference. And also, if we want to capture something by value and capture something by everything by value, but with certain exceptions by reference, we have special syntax that first we give our capture default, and then we put the exceptions there. Works this way. I didn't do any testing here. It's just mostly for illustration. Also, I would say I don't recommend using the capture defaults because they make it's a bit harder to read, and my personal preference is to have explicit variable names in captures. But I just wanted to let you know that the syntax is available, and when you come over it, you don't get surprised. And another thing about capturing by reference, it's just, although it's possible to modify the values for the Lambda expressions that you use with algorithms, it's undesired and not recommended to use lambdas that have side effects. If you rely on side effects in your lambda, you start relying also on the order of invocation by the algorithm, and therefore in kind of underlying implementation of the algorithm function, and that's an indication that you are doing something wrong. And now I've got a bit of practice for you with the Lambda expressions. And in order just to get the taste of how it works and basically take advantage of our very first algorithm, and which we already learned, and all the stuff we learned about the Lambda expressions, I would recommend to write a small program which will have a function where I can provide an additional a vector and an additional parameter of the threshold, and it's gonna count how many numbers are greater than the threshold. And I'm gonna give you probably 10 minutes to try doing this exercise, or you can use this as a break, and let's come back at 20 past 7 London time, basically in 10 minutes. And meanwhile, feel free to ask questions on Slack or maybe on YouTube. All right. 10 minutes have passed. I hope you had a chance to try it for yourself, and I hope you succeeded or at least got close. That's going to be my suggestion. Basically, it's very similar to what we had for just count positive, and we pass an additional argument, which is the reference number. We need to capture it so we can use it in the Lambda for comparison. This const is actually unnecessary. It should be just int, and then we can compare the entry with the reference. That's it for this example. And now we're gonna go on really entertaining journey with trying to improve our solution of palindrome detection. To remind the problem, palindrome is basically, last lesson it was a word which reads the same in both direction, forward and backward. And today we're going to tackle sentences which are or phrases which are palindromes. And these are first two examples. As you can see, it has capital letters, and we're going to work with this. It has spaces and punctuation, and we're also going to work with this. But we need to make sure that our solution still works for the cases which we used to support as all lowercase, and also we can test it for a word. Basically, it's a good practice when you start writing the test. You start with something simpler, and you always make sure that for simple cases your test works, and if it works for simple cases, you can move on to some more complex cases. Therefore, it's probably not the ideal ordering, but at least all the simple examples are here. And therefore, if I change something in my function that it stops working as I expected, the simple examples will indicate it to me. Therefore, here we know that these words to be a palindrome. Also, last time I had a big miss in my test, as I didn't have any word with even number of letters. Therefore, here it is. Noon is a good example. We still make sure that persimmon is by any means is not a palindrome, and as we now start working with punctuation, we make sure that, for example, we stick to the notion that an empty string is a palindrome, and let's just agree that whatever other characters which are not letters or digits we put there, we just ignore them, and basically everything reduces. If there are no such things as letters or digits, we reduce it to an empty string, and then consider this empty string a palindrome. As I said, is an empty string a palindrome is a philosophical question. It should read the same in both directions, and it kind of does, but also does it actually read, and therefore out of scope. Let's agree on this, and let's move on. A solution. First, basically, my plan is that I'm going to show you the solution. It's going to look scary. There are going to be very many unfamiliar things, and I'm gonna speak through it briefly, and then we're gonna decompose each element of the solution and go through the details, and then we will assemble it all back together. So the idea of demonstrating the original thing is basically just to give an overview. Where do we want to get, and then we will be able to just actually speak through the details, and then I will bring this back so we can revise it. All right. basically, the approach I've taken here, now our function doesn't take the argument by the const reference. Now I take it by value. Therefore, we immediately get a copy because we have to, like, I'm going to modify it. I want to start with removing all the characters which are not interesting to us. And that's a very tricky thing here. There is erase remove or remove erase idiom which I use, and we're going to talk through this. And what we do is we go over the string and we remove all the characters which are not alphanumeric, and I will explain what this function does. And then we got the string which contains only of the characters of interest, and we do apply the algorithm as Lauren asked, are there any non-unary predicates? And this is an example where we use a binary predicate. The difference between binary and unary is obviously it takes two arguments and still says you yes or no. And in this case, it says yes if the characters compare the same when they are reduced to the lowercase. So that's the plan. The last bit is what this half-length thing, and as we already discussed in the previous lesson, you don't need to compare the entire string when you are checking if it's palindrome. If you go till the middle from each side, then it's going to be enough. And if it's of odd size, you kind of don't care about the middle character. All right, now let's go and decompose it. And first I want to talk about the thing which we used in the previous example about counting positive numbers and counting numbers which are greater than. It's count and countif algorithms. They're kind of cousin algorithms, I would say, because basically they do the same thing, very similar syntax, and one is taking a reference element and count the same, like the elements which are equal to it. And if you want to do some kind of more just a different comparison, which is more complex than exact equality, you will have to pass a predicate. And in this case, the name of algorithm changes. It's count if, which is basically if predicate turns to true. If predicate says yes, then like we increase our counter. And the example itself is pretty simple. We count how many bananas we have in our fruit basket by the first example. We look at the entries which exactly equal to banana, and the algorithm returns us. It takes a pair of iterators and returns us a number, how many elements matched the equality. And the cousin algorithm countif takes the same pair of iterators, but here as a predicate I asked how many fruits have the size 6, and size means size of string in this case. And by a coincidence, we've got 6 or greater, and in this case we've got 3 fruit which are exactly 6 and persimmon which is bigger, and that's our answer. 3 plus 1, 4. And why I wanted to show this, it's that this thing about something and something if is a very typical pattern, and we're also going to see it with the next example about find, and you also could have noticed it with remove if. They seem to follow the similar pattern. If you are fine with equality, you use count to find. If you want a bit more exotic predicate, you use count if. Apart from this, they are identical and work the same. So I will briefly go through the find example, we've got the same fruit basket, and we want to see if there is an apple in it, and we use std-find. We pass the range of the iterators, and for find, it's not find if. We pass the exact value, and first, what's important about find and what does it return? It returns you an iterator, a first iterator, which points you to the element you were looking for. And if the element is not found, as I show by the next example, it returns the iterator which is equal to the end of the range. That's basically, it's an important idiom to remember. It's often done. You try to find something in a container, in a range, and then you check if it's found or not by a boolean, but comparison with the end of the range. If the find algorithm wasn't able to actually find the element, it will return you the second argument, the end of the range of the search which you have passed. And what's important here is, for example, when I'm looking for an apple, I use a require statement to check if apple is there, and then I can dereference my iterator, and yes, I see that it's actually equal to apple. And the thing is, I wanted to remind about require thing. If require fails in unit tests, the tests won't proceed, because basically if this wasn't the case, if apple iterator would be equal to end, it will be looking at the memory past the end of the last element of the fruit basket, and therefore dereferencing it would be undefined behavior, and that's what we should be mindful when we are writing our tests. So first, just also in your code, before dereferencing the iterator, make sure that it actually it was the lookup was successful. And Lauren and Slack is asking about the difference between string find and find on iterators. String find is kind of it has a bit weird syntax, as it returns you a position. First, it works with numbers, not iterators, and it returns you a position. But also you can basically on strings you can use standard algorithms, and from the point of efficiency, as in algorithm complexity, it's going to be the same. It's going to be quite efficient, but the syntax will be uniform, because on all the other containers, when you use find, it's all this logic with the iterators, and with strings somehow it's indices and this npos for simple not being for a symbol or a substring not being found, and it kind of looks a bit special. And also there is a reverse find for the strings, and here you want to do reverse search, you just use reverse iterators. So you do use cr begin and cr end in this case. Just don't forget to make sure that both of the iterators are reverse, and the fact that when you're checking if the element is found or not, if you're looking in the reverse range, you also need to compare with the reverse end iterator. And as the comment at the bottom mentions, there is also a cousin version of find find if, which takes a unary predicate, and the behavior of the output values is exactly the same. That's all about our basic things with find and count. And now I'm gonna talk a little bit about text transformation that we do. And here are a few helper things which we used. One was called isAllNum, which is short for is alphanumeric, and another one is toLower, which converts a character to lowercase. And the first one we use for filtering out things which are not our interest, which are spaces, punctuation, and any other characters which we can find as input, and only leave us with letters, both lowercase and uppercase, and with digits. And this example illustrates that it's returning Boolean, true or false, and I'm not exactly sure because it's a C algorithm. It might return integer, which just converts to a Boolean, but if you write like in this idiomatic way, it doesn't matter much. And another one which we're using is toLower. That's the trick basically to do the case insensitive comparison, because by default lowercase a and uppercase a don't compare equal to each other, and in order to do this comparison, we bring them both to the same case. Doesn't matter upper or lower. I chose lower, and in this case, if the outcome of toLower function is identical, that the characters mean the same letter but maybe in different cases, and toLower doesn't have any effect on other characters outside of the alphabet, which I also try to illustrate by this example. And both of those live in C type include. C in front gives a hint that it comes from old C times, pre-C++ times, and it has a bunch of other helper functions, most of which suspiciously have exactly 7 characters in their name, with only one exception for hexadecimal digits, and most of the names are kind of self-explanatory, as we can check if something is either a letter or a number. Is alpha is for letters, is digits is for digits. Alphanumeric is basically letters or digits, not numbers. Hexadecimal digits, punctuation marks, space characters, which probably also include tab, and then lowercase and uppercase, conversions to lower and to upper. To lower and to upper are the only things which return not Boolean. The rest are immediate, like you can call them predicates because they tell you yes or no, and these take, as far as I remember, an integer and return an integer. And if you need to make it a character, you need to wrap it into a function. If you need to make it a char type, you need to wrap it into something, and that's what I needed to do in my further examples. So that's like all what we need today for the helper functions to work with text. And I have to admit, C++ is not very helpful with these text and character processing functions. And if you do a lot of more complex text processing, you may want to look for other libraries, and there are some extensions in Boost, or like I can imagine that there are better string and character processing libraries out there, but for our purposes, this set appeared to be enough. So next thing, which haven't been mentioned before, but spoiler alert, you might find it handy for the home exercise, is std transform, which is a very important, quite generic algorithm, which applies a transformation function to each element of the range you have passed. And in this example, I illustrate how do I convert a string of characters into lowercase, and because I cannot pass for some legacy reasons to lower immediately as a conversion function, I just declared a function which takes an assigned character instead of an int, and then I apply transform function. I call std transform. The first two arguments it takes is the iterators of the input range. Where do we start? Where do we end? And the third argument is the beginning of the output, and basically this is an iterator which is going to be incremented after each element is being transformed. And in this case I use my input range and output range are the same. So basically I'm replacing the characters in my mixed case string variable, and therefore you can see that the variable has changed its value. So the because we, by the size of the input range, we know how many characters we're going to process, therefore we need only one iterator for as our output, and the last argument is the transformation function. Although today all my examples have basically convert a type into the same type, it doesn't necessarily need to be the same, and I can, I don't know, convert a character to an entire string which has this characters multiplied or something else, or any type of object I could imagine. And the same example, as long as basically my output container can store that type. And the next example just demonstrates how do I use output which is different from the input. So I created my mixed case string constant, therefore the compiler won't allow me to modify it. I have the same transformation function, char to lower, and here I have two examples for you of how can I make the output. One way to do it is because I need to make sure that I have actually space where I write these things. In the previous case, I did have this space because I was just transforming the characters in place. Here I have created a new string, and I need to make sure that when I'm transforming the characters, I'm writing there into the memory which allows me to write them there. And I used the string constructor which says how many characters should I allocate, and also I just need to provide a default value. I chose space, it could have been anything, and that's how I invoke the transform. Same input range, and as output, start of the output position, I provide the begin of my pre-allocated string, and then I pass the same function, and then you can see my pre-allocated strings turns into the transform string. John has a question, what gets returned if the character is not alpha, as is not a letter? If I get the question correctly, I'm gonna go to this example of Tulova, and basically here, if it's a digit, we just pass it through. And same with if it's basically anything which is not a letter is being passed through, only the letters are being transformed in this case when we use tool-over. And here in mixed case also we can see that space is just untouched and processed as it is. Basically only the uppercase characters are being affected. Back to this example, we talked about preallocated string, which is like safe example. What's a very typical mistake, and what I'd like to warn you about is that if you have an empty string, if you just basically declare a string and this is not a valid syntax, sorry, because I'm stupid, because here I should have dot begin to make it an iterator. This won't compile anyway, but if I put if I uncomment this and put dot begin after allocated during transform, this is gonna compile, this is gonna run, and this may or may not crash, but I'd better not to reason about it because it's undefined behavior and it can do anything. And as I already quoted Marshall Clow as, it can delete a file from my computer, it can print something, it can make my cat pregnant, and I still don't have a cat. So just don't try to reason about undefined behavior. Don't do bad things, don't do dangerous things. And that's another way if you want to save yourself from preallocating a string and also filling it with dummy spaces or other dummy characters. There is a very magic helper called back inserter in the standard library, std back inserter. And when you have to provide an output iterator for transform or for some other algorithms in the future, what happens here? Back inserter produces an iterator which will, on each dereference and write, append an element to our container, so it will request for a memory and store the element in the container. For vector, and I believe for string too, it's going to be basically equivalent of calling pushback on each character from the original mixed case string. And this code is correct. It works as expected and have no undefined behavior. And also because of the way how, for example, strings and vectors are organized, we are likely to have only a logarithmic number of allocations here. And I won't be surprised if the modern compilers can figure out even something smarter. But that's another way to output into a container which is different from our input container using the back inserter. And I wanted to share this, so if you meet it, you won't be surprised. Loren is asking on Slack if it's an example of functional programming. Yes, I would say so, and I will also, like, by the end of the lesson, I will provide some additional material for you to look, to watch, to study, and like one of the talks which I am going to recommend is going to be talking more about the functional programming examples and also why transform is important and what are the other algorithms if you are interested. While going through the course, we will meet a few more examples like this. All right, done with the text transformation and also with std transform, and also as for functional programming, transform is not only for text transformation. It's for transforming anything to anything, any type to any type, and yeah, that's why it's basically one of the fundamental algorithms, and can be considered as an example of functional programming. It's not, I would say, very convenient with the current implementation of C++, as you really, like, it's not convenient to chain the transformations, for example, and you always need to make sure that the memory is there. But this problem is addressed in C++20, which we are not talking about at the moment, because the widely used standard is 17 at the moment, and I'm focusing on what can be used. But also, like, if you study C++ ranges and what they allow you to do, is just more beautiful and more entertaining and much more easier to use. But for the purpose of this course, is just out of scope. So to the next bit, which we used in our palindrome exercise, and I'm going to be talking about remove and erase idiom, and I want to come back to one of the exercises we did when we were talking about vector, and we were talking about iterators, and also iterator invalidation. You can remember this piece of code, which is not very beautiful, but that's the way we have to do it. What happens here is that our goal is to remove all the persimmons from our fruit basket, and erase persimmon function is the way to do it. Also, just a digression, but after writing this piece of code, I wasn't able to buy any persimmons in my local supermarket, and it's a very weird coincidence. So what's very special about this example is that we don't increment our iterator in the normal way as we do for loops, and we do it only in the case if it's not persimmon and therefore it wasn't erased, and if we need to erase it, we get the iterator from the erase function, which is also error prone, and there is an algorithmic solution. Algorithmic is in terms of standard library algorithms for this, and basically that's erase persimmon function rewritten with algorithms, and I've broken it down here into two steps: invocation of std remove, and then using the vector arrays, but on a range rather than on per element. You can, I'll just go back one slide to show you. Here I pass only one iterator, and therefore I remove only one element. And here I pass a range of iterators from where to remove to basically the end of the vector. And it's more efficient, as removal from the middle of the vector requires the linear shift of all the other elements, while here we can erase everything at one go, and therefore it's just fewer steps. And first, let's talk about why do we use basically two steps. The reason is what std remove does for us, and it doesn't change the size of the vector. In our case, it applies to any container. It goes over the container and groups the elements which we need to keep at the head of the vector, obviously keeping the ordering, and basically drops all the unnecessary elements. There is also remove if case inversion, which takes a predicate, and in this case it's going to be dropping all the elements which satisfy the predicate, and collecting together, grouping together the elements which didn't satisfy the predicate and therefore should stay there. And when all of the elements which supposed to stay are compressed, the remove returns the iterator of the vector elements which have kind of undefined values, and they need to be trimmed. And we do it with the second step of of arrays passing it a couple of iterators rather than one iterator. It's very widely used idiom, and I'll just turn the slide usually because we don't need to declare the variable for the first iterator. We can consume it at the spot and do this in one expression. And I believe it has been addressed in the next edition of C++ standard, but as of C++ 17 we still have to do vector arrays with remove invocation, and there is something like erase if or erase and remove for in the new standard. And as we're doing it for now, I just needed to explain this idiom and what's important about this example. Even there is going to be one invocation for erase and remove in the next standard, it's still there are many cases where one algorithm just gives you a position and second algorithm can consume this position, and that's why being able to operate with iterators and being comfortable with them is important. And that's why I decided to bring up this example and spend some time here. That's basically all about removing the arrays, and we are coming to the last bit, which is making sure that the string after all the transformation is reading the same way back and forth, and we are doing this with std equal algorithm. If you remember my previous solution, I was just previous solution for the palindrome problem, I was just declaring a new string which was constructed of two iterators which were reverse iterators, and therefore I was basically constructing a reverse string from the reverse iterators. And the disadvantage of this solution that I was allocating additional memory for the string, which I actually don't need, and I can just use the equal algorithm with the reverse iterators and do all the comparison in place. And here I have a few examples. How do I invoke the equal algorithm? I basically pass the range, the iterators which designate the first range which we are comparing, and iterators which designate the second range which we are comparing. And these ranges are not equal because the characters lowercase w and uppercase w are not considered equal. Therefore, std equal returns a boolean which is false. But in order to be more flexible, we can pass an additional argument to this algorithm, which is a binary predicate, which says yes or no for two elements. In this case, the elements are the same size or the same type, and what we do is we do equality comparison of characters converted to the lowercase, and for the given strings, the outcome of std equal is going to be true. Meanwhile, there is a question from Loren on Slack. If I need to do sum of squares of elements of a vector, would I use std transform? No, because this will, like, the only way to do it is having side effect in a variable which we capture by a lambda with the transform, and there is a better algorithm which is called accumulate, or another option will be reduce, and like I'm not going to cover the difference between them, but basically, yeah, there are two options for approaching this, and they're exactly for the purpose. So reduce is another term borrowed from the functional programming, and it goes over all the elements and collapses them to some result, and accumulate also serves the same purpose, and by default it will do just addition, but you can modify the thing which does the addition and get the sum of the squares rather than just the sum. That's the way I would do it. Getting back to our equality, there is another important thing, another call out, which I'd like to make about equal. It has another overload which takes, for example, here I created different strings. I'm not talking about predicates here. I'm not talking about the like fancy comparison. I just want to show that there is another weird version which you probably like, which is there for historical reasons, but which you probably don't want to use in general unless you really need it. I discourage the usage of it. There will be some examples as like, for example, you're reading from a stream or something, but for most of the range comparison, when you know the end, please use the version which takes for each range a couple of iterators. But there is also a version which takes for the second range only one iterator. And here what we can do is that the example about 3 iterators instead of 4 will is going to be on the previous slide, because here I'm only talking about 4 iterators example, and it shows that in addition to comparing element to element, this 4 iterator example is going to also do the size comparison for you, and bear is no way equal to a duck. But if we declare a very dummy binary predicate, which for any pair of characters says yes, they're equal, in this case, bear becomes equal to a duck with our amazing always equal predicate. But if we take a long cat, a character from internet memes, you can see that even if all the characters until we do comparison compare equal, because in one case we stopped going over the bear characters, but apparently long cat is long and therefore has additional characters to keep going, the equality comparison fails although the characters have compared equal. The trap is with the 3 iterator version, and here I just compare a duck and a duckling. Counterintuitively, the duckling is longer than a duck, but bear with me. The idea that if I use 4 iterators version, so each range is designated by 2 iterators, the beginning and the end, they are not equal, because std equal detects that in one case we reached the end of the range, and in another one like we still have characters to go. But there is also a version which takes only the beginning of the duckling range, and so the end can be omitted. And this is correct to use, for example, only in the case if you have done the size check before, and you know that the sizes are equal. Or another example maybe if you are like have some streaming input iterator here, and therefore surprisingly, although duck is not equal to duckling, this std equal example is going to return you true. And there are many algorithms in the standard library which have basically versions for both like one iterator or both 2 iterators to designate the second range. And I want you not to be surprised when you come over this, and also if you have funny bugs you don't get surprised and know how to fix it and know also why it works. And what's more scary, like there is another way to step on undefined behavior. If you pass the duckling at the first range with the begin and the end, and only the first iterator of the duck, eventually after the first four characters, you'll try to read the past the end of the duck string in the equality, and reading past the allowed memory is undefined behavior, and there is nothing good about it. It's dangerous. There is a question from John. If the comparison goes through the entire string or stops when inequality is found. I'm not sure if it's exactly specified, but I would expect it to stop in the first character for the purpose of efficiency. And I expect standard library algorithms to be rather efficiently implemented. I don't see a reason why it would keep going after the first mismatch has been found. And we basically are done with all the details which we wanted to go through, and now it's time to revise our initial solution and make sure that all the things which are happening on the screen are clear and familiar. And I will encourage, I will just give some time to digest this, and if you have questions, please ask. And if you have questions, please ask, and let's just make sure that everything is clear here. There is a comment from Tristan on chat that yes, equality stops when the first mismatch is found between the containers. So back to this example. We take the phrase by value so we can modify it, and then we use this is where I use a Lambda expression to declare a predicate which identifies all the characters in the string which are not letters or digits, not alphanumeric. And then I use a remove if algorithm to remove these characters which are not alphanumeric, as just basically collect to the head of the string all the characters which are alphanumeric. And then I, with erase remove idiom, I make sure that the string I've got only contains the characters of interest. And then I'm gonna do equality. One goes from the beginning to the middle, and as I mentioned before, we don't care about the very middle character if the string size is odd, because it's anyway going to be equal to itself. So we go to the middle of the string with the begin iterator and begin plus half of the length, and we also take reverse begin and add to it half of the length, and these are two ranges which we compare. We didn't do any transformation for uppercase characters, and we gonna do this in place during the comparison, and that's our binary predicate, which takes character from each range and make sure that they are equal. And then std equal, if std equal returns true, this means that the first half and the reverse second half have the identical, have the same characters in terms of if they're with case insensitive comparison. And that's our cool function for checking if the phrase is a palindrome. And that's basically it for this deep dive on the algorithms. On the other hand, our very first introduction to the standard library algorithms. And thank you for going through all these like enormous details. I can imagine how much of the information has been here and of new information is here, and thanks for going through all of this for you. Like in a few minutes we're gonna start summarizing and wrapping up, and then like I'll give you another similar exercise to practice for yourself. At the moment, like first there is a question from Lauren on Slack. Any tip to read the specification, how to read the specification of STL algorithm on CPP reference? First, yes, cppreference.com is the place I usually go to look at it, and usually the ways to like there are multiple overloads listed, and they're all numbered, and if you start reading it more, you will start recognizing a pattern. As I said, for example, there will be, for equal, you expect a range, and therefore there are going to be one iterator and another iterator. Usually some iterators come in couples, and all of these various overloads are enumerated, and then below there is an explanation which tells how the overloads are different, and what do they return, and what they are like special conditions, and so on. And also there is an example below, and sometimes it's easier to start with an example and then see what are exactly the overloads which you want. Lauren is posting an example of like there is execution policy and such things as at this moment you probably don't need to worry about the execution policy, and mostly look at the things which have forward iterator, or just in general an iterator as the first argument. Policies are for parallel algorithms, and as far as I'm aware there is no good implementation available in widely used compilers for parallel algorithms, and basically although it has been accepted into the standard, you don't need to worry about it now. And also in general, like parallel computation is past the initial things you need to know about it, and as applies to many things, you come to the parallel computation when you already exhausted all your options with the normal stuff. And for most of the things we are doing in this course, you don't need to worry about parallel computation, and most of the things can be efficiently done in a single-threaded way. So wrapping it up, I will probably just give a few minutes for final questions on this example, and then we're gonna wrap it up. I don't see any other questions, so let's continue. We've gone through all of this, and we've talked today about algorithms. We had our first example, and I encourage you to learn algorithms and try applying them to your solutions. They make your code more expressive and easier to read. They tell you or other reader what exactly you are doing in the function, rather than the details how you are doing it. and I appreciate like even for my code coming back to it in 3 months. I appreciate, oh yeah, this reads better, and I can catch the idea much faster, and it is an advantage if you're only writing for yourself. And that's why I encourage you to write more expressive code and study the algorithms. Also, we had our very first introduction to Lambda expressions, and I showed you how they work with STL algorithms, and I think they were great with STL algorithms. And I gave you a few more details, how can you apply them, how to use captures. There are more things like you can syntactically and practically do with captures, but as I didn't have use cases here, I decided to omit them, and I just might extend a bit later the examples which I've given if we need some other tricks. And also, although there are like more than 100 algorithms as counted by Jonathan Baccara, they are really similar, and as long as you recognize what's available there, the same principles apply, and it might be a bit trickier to start with them. And the start is going to be slow, but as soon as you learn a bunch, it's going to become easier to use and easier to read the code with algorithms. And if you pick up a new algorithm, it just follows the same principles, so you can use it straight in place. And the rule of thumb which I would recommend when you're writing a for loop, try to think, can you come up with an algorithm for the idea of the algorithm for it, and then try to look it up in CPP reference, or maybe just Google something for this, and Stack Overflow answer comes up, and in general see if you can replace a for loop with an algorithm. John is asking about for each, and it's I think I've seen it in Jonathan's talk as for each applies a function to each element, and basically because it ignores the return value of the function. The only thing it can do is side effects, and side effects are not great, and therefore probably in general like for each is not a good idea in itself, and not necessarily that like if you can apply it you should, because it works on the side effects, and side effects are considered not a good pattern for the expressive code. And Loren has a question. If he approaches a new problem, is it natural to do a first draft with a loop, and then when it passes the tests, update it to algorithm? Sometimes this works, but I usually prefer the opposite. If I just have an idea like in my head or in paper, I will try to look it up, because the advantage of using the algorithms is that they save me from off by one errors, for example, as like I exactly know where do I start, where do I end. They handle the edge cases like empty vectors and empty strings, and maybe some other edge cases, and therefore if I need to manage many indices and starting points and ending points and some conjunctions of them, I may make mistakes and just spend more time in bug fixing and testing and so on, rather than just writing it straight with the algorithms, and basically things may just work with algorithms. So I may do some like drawing or whiteboarding in order to express the loop which I want, but after this I try to see if there is an algorithm, and if I cannot find an algorithm and I really see that the for loop is the only way, then I go with the for loop. But writing a for loop usually implies I need to be more thorough in testing the edge cases as the empty array, the array of one element, odd numbers, even numbers, and so on and so on. That's my approach. I've got a home exercise, which is going to be anagrams, kind of similar to palindromes, but also different. And the exercise is going to be to write a function which takes two strings and says if one is anagram of another, which means that if it has exactly the same letters, but just in a different order. I have a few examples for you here. One is borrowed from Harry Potter saga. Another one is just because we're in London and we can talk about tea and Great Britain. And if I don't have the third example, the function a function which always says true would pass the test, but it should not always say true. Therefore, obviously, if strings are not anagrams of each other, your function should fail. That's gonna be the exercise until the next time. Most of the elements have been already demonstrated to you in this lesson. You may want to you will probably need to look up some other algorithms which will help you in this exercise, but that's also part of the exercise. You go to CPP reference or you go watch the talks which are going to be at the next page, and you will gain some more knowledge about all the the variety of algorithms that which are available in the standard library. I'd encourage you to do more practice with this. And for the future lessons, I will think about more exercises which will allow us to engage with more algorithms. And speaking of further, not reading but watching, I already brought up Jonathan Bacara's talk about 105 STL algorithms in less than an hour. And it's a great talk from the author of the STL algorithms map, who goes through all of them and basically explains why they need it and what they do and how to use them briefly. And I hope the basics which I've explained today is going to be enough to get an idea of how to use them. And there is another great talk from the last year by Connor Hoekstra, and also he has this is a talk from the conference, but he also has a YouTube channel, and I'd recommend to check it out. The talk is called Algorithm Intuition, and Connor gives a lot of examples why he's fond of algorithms, and he also gives examples in different languages, and then basically he tries to encourage you to develop the intuition, how to find the right algorithm and how to apply it. And he demonstrated by starting from simple examples and building up to more and more complex. And if you have time, I also recommend to watch this talk. It's in two parts, but it's totally worth it. Also, he is a great presenter, and probably the first half of the first part is really entertaining, and he gives a lot of encouraging examples from other people, and refers to many other talks about algorithms, and it's very inspirational and gives an idea how deep the topic is and why it's interesting. Also, speaking of practice, because our next session is going to be, if I'm not mistaken, on the 7th of April. So before I see you next time, they're going to be a very important event for practicing in programming and problem solving, which is called Google Code Jam. And they're going to have on the Saturday, April the 4th, they're going to have the qualification round of their annual contest in problem solving, like algorithmic programming. Qualification round is not hard, and also they give you more than 24 hours to solve the problem, so you can do it in your own pace. And the problems are nicely phrased, they're easy to understand, they have a bit of complexity there, so you will need to think a little, but they're approachable. And if you haven't done things like this before, I really recommend to try it. If you are doing something like HackerRank or Lead Code or something similar, the difference between those and Google Code Jam, one is just they really put effort into make the problems nice and fun to read and fun to solve. And because there are only few problems, it's just they can put more effort into it. And another fun part of it is that it's a competition happening in real time, and hundreds, thousands of people are trying to solve the same problems with you, and you'll see where you rank. And like if you have never done it before, you'll get some like starting point, and you can have a goal to improve the next year. I enjoy it, and I basically this is one of the motivations for me to study new things and study the algorithms and try to like write the code which works correctly in the first place, because some of these competitions are quite time constrained, and I encourage you to try it yourself. And this is it for now. We are done with the first at least first remote session on the standard library, and I appreciate you being with me here today. Any feedback you have, please come on Slack and share with us. If you are not registered yet, make sure to register and come there. Most of the announcements come there. Also, the conversation is happening there, and also we have a Patreon, and we basically, if you like what you are doing, what we are doing, and if you find it valuable, please check out our Patreon account, which we you can donate a small amount there, and we are a charity. We don't get any money ourselves from it, but we can use this, for example, for the new equipment, or this may be helpful for like if we go for webinar solution, and we will be able to afford some paid options here. And we appreciate you staying with us. That's it for today, and usually we head off to a pub, but today it's only gonna be, it can be virtual pub, which we haven't figured out yet. Therefore, I'm gonna wrap up here. Thank you for being on the stream and asking questions, and I will see you in 2 weeks, and I hope we have a better solution, so I will be able to hear questions from you in real time and with your real voices. That's it from me today. Bye, and have a good evening.